Let's practice some Newton's law of cooling problems together. Now, if you're learning about Newton's law of cooling, that means you are working with logarithmic and exponential functions, so make sure that that is what we are applying our knowledge of today. So here's our situation. You are driving on a hot day when your car overheats and stops running. It overheats at 280 degrees Fahrenheit and can be driven again at 230 degrees Fahrenheit. If R is equal to 0.0048 and it is 80 degrees Fahrenheit outside, how long, measured in minutes here, do you have to wait until you can continue driving? Alright, so let's start with our formula for Newton's law of cooling. Now this right here is our formula, where T sub 0 represents our initial temperature, T represents the temperature after T minutes, T sub R represents the surrounding temperature, R represents the substance's cooling rate, and this T represents the time measured in minutes. Now, looking at our specific situation here, we know that the initial temperature here is 280 degrees at the beginning. We know we want to cool this down to 230 degrees before we can drive it again. This R value is going to be 0.0048. That's going to be that cooling rate. And then what is the surrounding temperature? Well, the surrounding temperature is 80 degrees outside. The question does ask us how long, so we are looking for T, or lowercase t, which is measured in minutes. So let's go ahead and solve this problem now. Here is our original formula, and let's go ahead and substitute in capital T here at the beginning is going to be 230 degrees Fahrenheit. Let's put that on the left side. That's going to be equal to, the initial temperature we said was 280 degrees, so let's go ahead and plug that in, 280. Let's take away T sub R, or which is going to be representing the surrounding temperature. So looks like it is 80 degrees outside, so minus this 80. Let's go ahead and put the end of the parentheses there. We're going to multiply this by E, which is that value of about 2.71828, so on and so forth. This is raised to the negative RT power. So R is going to be 0.0048. We're going to multiply that by T, which is actually what we're looking for. So let's keep that lowercase t the same up here. Let's go ahead and add on T sub R again, which we know is the surrounding temperature, and that's going to be 80. All right, next, let's just go ahead and simplify this a little bit here. Let's go ahead and subtract these. So on the left side, we're still going to have 230, and that's going to be equal to 280 minus 80. That's going to be 200, and that's still going to multiply by this e to the negative 0.0048 times the amount of time measured in minutes. And let's go ahead and add this 80 on at the end, the surrounding temperature. Next, let's go ahead and move this 80 to the other side just so we can combine like terms. So subtract 80 on both sides of this equation. And when we do that, we're going to get 150 on the left side, and that's going to be equal to 200 multiplied by e to this negative 0.0048t. Then, since we're multiplying 200 by this e to this power, let's go ahead and divide both sides by 200 so we can isolate what that exponent or that power looks like. On the left side, 150 over 200, that is just 3/4. I'm going to use a decimal though. I'm going to use 0.75. That's going to be equal to e to this negative 0.0048t. Now at this point, we really need to get this t down from the exponent, so in order to do that, we're going to have to use a logarithm of some sort here. Now we have base e for our exponent or our power, so let's go ahead and take ln, or the natural log of both sides here, right? So taking ln is going to be the inverse of e, so let's go ahead and do that here. So on the left side, we're going to have the natural log of this 0.75, and on the right side, we're going to have the natural log here, or ln, which is base e, right, to the negative 0.0048t. All right, so now if you plug this natural log of 0.75 into a calculator, because you can't do that by hand really, you're going to get roughly negative 0.2877. Okay, that's what that's going to be on the left side. And on the right side, keep in mind what's going to happen with this exponent. Now remember, one of our log properties is that when we have an exponent here in a log, that can actually come down in front of what we have here for the logarithm. So if we move this down, this is going to be negative 0.0048t, but it's no longer an exponent, right? Because we move it down in front, and then we have this ln of e. But what is ln of e? Try to recall that this ln of e is actually just equal to 1, so you're just going to multiply by 1, or it just cancels out. And now for our final step here, let's just go ahead and divide both sides by 0.0048. That way we can isolate and solve for whatever this t value is. So dividing both sides by this r value, we're going to get t is going to be roughly equal to 59.9375. Okay, and so what does that mean in terms of this problem? Remember, t, this lowercase t, is representing time in minutes. So we can conclude that you must wait about 60 minutes or an hour until you can continue driving. Let's try another one together. And if you're feeling good about this, feel free to just pause the video and try it on your own, and then unpause if you want to see how you did. Alright, so in this situation, you are cooking some food on the stove. When you take the food off the stove, it has a temperature of 200 degrees Fahrenheit. The room temperature is 75 degrees Fahrenheit, and the cooling rate for the food is R is equal to 0.054. The question is, how long, measured in minutes, will it take to cool the food to a serving temperature of about 100 degrees Fahrenheit? So again, just to help keep things organized, this is all our information and Newton's law of cooling formula that we need to use. And then let's start with identifying a few things here. So the initial temperature of this food that was cooked is going to be this 200 degrees Fahrenheit. So that's the initial temperature. And then we need to look at this 75 degrees. That's going to be the surrounding temperature of wherever we are here. So 75 degrees, that's going to be the surrounding temperature, or T sub R. Then you have a cooling rate. This R value is going to be this 0.054. Then the question is how long. So again, it's a very similar question in terms of us looking for how long in terms of minutes. So that's going to be that lowercase t measured in minutes. And then finally, we are given this 100 degrees. That's what we're looking for in order to be able to eat it. That's going to be the final temperature here. So that's going to be 100 degrees. That is going to be our capital T, or the temperature after t minutes. All right, so here is the original formula. Let's go ahead and now substitute some values in. So this capital T on the left side is going to be 100, because that's the temperature we're looking for to be able to eat this food. It's still too hot at the beginning here. That's going to be equal to T sub 0. The initial temperature here we know is 200 degrees. So let's go ahead and plug in 200. And then what's the surrounding temperature of this room here? Looks like the surrounding temperature we know is going to be 75. So let's go ahead and plug in 75 here. So 200 minus 75 is inside the parentheses. Let's go ahead and take that and then multiply that by E raised to the R value. Now R is 0.054. And let's multiply that by T, since we don't know that's actually the variable we're looking for, all right? So we're gonna go ahead and add the surrounding temperature, which we know is 75 degrees. Next, let's just subtract this 275 to just make this a little bit simpler to look at here. So we have 100 on the left side, and that's going to be equal to 200 minus 75, that's going to be 125. So let's put 125 here. Let's multiply that by E to this negative 0.054 T. Let's go ahead and put T right next to it, and then add on that 75 afterwards. Next, to get the power isolated, let's just go ahead and subtract this 75 from both sides of the equation. If we do that, then 100 minus 75 on the left side is going to equal 25. So we're going to get 25 is equal to 125 times E to the negative 0.054 T. Next, to get that power completely isolated, let's divide the right side by 125 and the left side also by 125. Now on the left side, 25 divided by 125 is actually 1/5, or we can say that's 0.2. So on the left side, that's a nice decimal. 0.2 is equal to, and we're going to have E raised to the negative 0.054 T. Now at this point, you want to remember, how do you get that little t from the exponent down from being an exponent down to being just a regular t, not as an exponent? And this is where you're going to take a log of both sides. Now our base of our exponential on the right side is e, so we're going to go ahead and use ln, or the natural log. So let's take that of both sides. Ln of 0.2 on the left side is equal to ln of this e to the negative 0.054 t. On the left side, this natural log of 0.2, you got to plug that into a calculator. That's going to be roughly negative 1.609. And on the right side, think about what's happening over here. This exponent up here, we can go ahead and take that and bring it in front of the logarithm as one of our properties of logs we can do. So we can go ahead and put that in front. That's going to be negative 0.054 multiplied by t. And then let's think about what happens to that ln of e. You want to remember that that ln of e is just equal to 1, just because you have a base e, so that's going to just become 1, and we don't have to write it. For one final step, let's get t completely isolated. Let's divide by negative 0.054 on both sides of the equation, negative 0.054. And when we do that, we're going to have t completely isolated, so we can say t is approximately equal to, that should come out to 29.804. So in conclusion, it will take about 30 minutes for this food to cool down to a temperature of 100 degrees, which then you can eat it. So there you have two different practice problems where you are dealing with using exponential models here and taking logarithms on both sides of an equation. And we went ahead and practiced two problems dealing with Newton's law of cooling. So I hope you found this video helpful. If you did, please consider giving it a thumbs up. And as always, keep up the great work that you're already doing, and I'll see you in the next one.